going to see a little bit more practice. Some of one of the concepts I have presented this morning, and of course, so this will be not based on a tool. Actually, we can perform it using a tool, but it's so it's not so much advanced as in the previous speech, and the tool we presented is really well perfected, and it was so clear. So what we are going to experience is a little bit, it will be based on paper, and after that you can practice on the tool, and I will provide you the link. And just to start, I took the idea of the barbecue robot, actually. I just dig a little bit and it was already done. Sorry for that. But at least you can see that the concept is not completely, I would say, out of the air. And you can imagine that some people take it as a very interesting case study. And for me, it's also an interesting case study because what we can think about is maybe starting with the idea of, okay, let's say you are building this robot for the end of the week, and you have, which is not here, I think I found another picture with more explaining how it works. So it means that you have a camera, and you have a sensors for, of course, for the robot itself, for the robot arm, and you have a mission, which is cooking well, and depending on what you want to cook and things like that. I didn't dig a little bit if it's just a research project or if you can buy it. I'm not sure you can buy it, but I think it's just a research project. What we can think about is, okay, let's do it for the end of the week. What about any failures of such a system, and what are the hazardous situations it may lead? It may induce. What do you think about that? Just brainstorm a little bit, and then we will take 2 or 3 hazardous situations. So hazardous situation for the users, for the system itself. What can you imagine using such a device?
Sausages burning.
Sausages?
Burning.
Burning. Is it a safety issue?
No. Long term.
Long term, fire. Yeah. Fire of the system, or fire of the sausages. I don't know which one, but maybe it's possible to get some fire here. This is a safety issue, which if too cooked, I'm not sure it's a safety issue. So fire, okay?
Throw the sausage into the cook's face.
So not cooked. And then people are eating them, and then they might die because... Okay, it's another issue. Not cooked. Too cooked, not cooked. Or fire is more a safety issue. Not cooked, I'm not sure we can... it will be more a performance or something like that. If you cannot link into safety, meaning in terms of consequences, harmful consequences for the users or... Okay. It depends if you consider that the sausage is part of the system. Okay? If you buy it, or it depends where you buy it, and so on. Other issues.
Short-circuit of the...
Short-circuits, yes. So that's interesting. We are not exactly at the same level of fire. Okay, this is a direct consequence of using this system, and a short-circuit. Short-circuit, in that case, will be a failure of a subcomponent of the whole system, and it may lead and propagate to a failure of the service. Which type of failure if you have a short circuit? What can you imagine if there is a short circuit here about the mission, the robot itself?
Destroy the robot.
You destroy the robot. So then, what happens? The robot just freezes. It is a safety issue. Not really, if the robot freezes. But what can happen? Let's imagine if there is a short circuit here.
Unintended motion.
Harm?
Unintended motion.
Unintended motion. something like that. So then what could happen? Some, sorry? So you can throw the sausage, yeah? Into the air. That could be harmful if it's burning or if it's hot. Yeah, throwing sausages. And actually, it's one of the very classical hazardous events in industry. When you have some mobile manipulators throwing objects while they are manipulating them, grasping an object and throwing into the air. It's not so rare, actually. It's a real hazard. Yeah, so we said fire, throwing objects. Sorry?
Compress the object.
Compress the object. So let's say that here you have a tool, yeah, you can destroy the object itself. Might not be a real, it depends if you consider that your sausage is really valuable and it's it's an item of really important.
It's depending on which place on barbecue the hot dog is lying, because we can have different temperature. But actually, it's a question about energy transfer. In some places are higher temperature, in some places are more cold.
Yeah, but in that case, it's a part of the control system. It's a task of the control system to manage this different temperature. And we can use some cameras and thermic cameras or something like that to manage that. But
Color maybe, or
yeah, but
how does it work? Is it on color or on temperature?
I guess this one is based on a camera and image processing to determine the temperature of the barbecue, and then you have to configure it depending on the meat.
Another problem is a little safety bit of glass. People could lean in and point at stuff, and the robot might hit them.
Yeah, you mean might kick the user?
Yeah,
Or-
it might
Yeah.
do anything, yeah.
Yeah, for instance, yeah. This is something, it's not protected by fences. We cannot imagine that we are doing a barbecue with a robot with fences around, you install it in your garden, and then, okay. So the idea of the barbecue is actually also, okay, share the workspace with the users. So collision with users is part of the really important safety issues here. So this is what we call hazardous situation. I bring you this system, and then you have to analyze, okay, if I'm using this system, what can occur to the users or the robot itself or the environment? So we said we can throw sausages, we can set up some fire, we can have some collision, okay, and so on. So there are others hazardous situations. Now let's imagine that you have done it in 1 week, with some of you doing the mechanical part, the hardware part, the software part in 1 week. How can you guarantee that your system will not have some failures, that may be short circuits, but it could be a fault in the software or whatever, that the system is going to throw a sausage, for instance? How can you guarantee that? Even if you are using very good software developers and excellent PhD students making a lot of stuff around that, and testing and so on, at the end of the week, it's really, really difficult to guarantee that your system is safe. So what we can do, and because there are many causes. Let's take the sausage throwing, for instance. There are many causes of such a behavior. Failure in the software, failure in the hardware, failure in the electrical part, failure even in the mechanical part, the actuators and so on. So computing or calculating the probability of throwing a sausage might be really complex to establish, and it might be impossible to guarantee that this event will not occur. So because, yeah, and I didn't talk about the vision system. You are using a camera and vision processing and so on. So it's a lot of software and software that is impossible to demonstrate that it's correct by construction or even correct. So what is done it's done in industry, or it is done in also in today in more advanced system, is just to build. So you have your main system, the main control system, and you add a safety layer. The safety layer is here, or a safety monitor, it depends, you have different terminology. It is here to guarantee that some properties will be respected. And this safety layer is much simpler than the main control system. And the safety layer is here to guarantee that even if you have used some hybrid simulator, as we have just seen, even if you have used any fault removal techniques, you will keep your system safe. You will keep the system in a safe state. And this safety layer or safety monitor actually is something that is not so easy to find. And it's not so easy to determine. First, let's say for the throwing sausages, you want to add this safety layer. So it's a separated component from the main control system, okay? That is going to monitor that you are not going to throw any sausage. Which rule you want to put in this safety monitor? So you want to avoid that in case of any failure, you are throwing some sausage.
Maybe you can have another robot which will catch the sausage.
It's possible. The easiest thing is a catcher or bigger, like people around, or you just distribute some helmet to people, okay, around, saying, okay, we are going to barbecue with a robot today, make a strange party. But think about which properties regarding the state value you can implement to guarantee that the sausage will not be thrown.
Make sure that none of the motors inside the robot move faster than a certain speed.
So none of the
Motors inside.
yeah, but okay. So the motor, you mean the actuators here?
The actuators, yes.
Yeah, but if they do not move, you don't have the mission.
Yes, but it's the speed. You don't want them to move too fast.
Ah, you want to limit the speed.
Yes.
So in case of increase of the speed, at some point, you can decide, well, usually in a nominal behavior, the speed should be in that range. And if it's going out of this range, it means there's a failure somewhere. I don't know. It might be actuators, software, vision processing, or whatever. But I want to guarantee that the speed will not exceed the over limit that is required for throwing a sausage. That's right. This is what is done in industry, actually. And you have safety layers, which are basic layers, with a separate sensor for speed, and a very basic controller, which is often implemented with hardware, and just disconnecting and removing power from the robot. Okay, this is very simple. But now, yeah?
Usually in industry, every movement and every grips and everything are designed in normally closed, which means everything is closed or on break, and it only moves if something else happens. So if the grip is designed in normal closed way, it will never throw anything.
You mean,
even the signal comes.
you mean under certain circumstances? You have to describe.
So normally it will always catch what is in the hand, in the grip,
Mm-hmm.
and never let it go.
Yeah,
Everything is designed in normally closed, not normally open.
you can do that. It's the same as for trains where
Yeah, yeah.
safe state is closed. Yeah.
Yes.
So the question is how to react in case of failure. So detecting, observing the system, overspeed. Then how to react, how to recover. If we just shut down or switch off the power in the robot, it could be kept in a safe position. But in case of the sausage, if you just shut you just stop the robot while it's moving a little bit faster, but on the just above the fire. Then it will stop, and if no one is around, what's going on? Burning, fire, and maybe the robot will go on fire and whatever. So what is a safe state in that situation? When you remove power from actuators, some of robotic actuators just stop and still in position. You cannot move them. But if it's just above the fire, it could be harmful. So it's not really successful to put it in a safe state. There are other actuators. When you remove power, it just go in 0G mode or releasing powers. But in that case, you will put the sausage directly into the fire, and then it could induce some hazardous situation also. So observing here is not too complex. Speed. We can put some extra sensors on the robot. But how to react here is not so simple. Okay? Now, the rule itself, which say, okay, if I have a speed which is more than, I don't know, 2 meters per second or something like that, centimeter per second, I just stop the robot. The rule is quite simple. Now, which one was the collision? Collision, so you have self-collision of the robotic arm itself, collision of the robot with the barbecue itself, or collision with the users. And in that case, the safety rules, the observation might be more complex first than just a speed, because it will require maybe vision, other sensors around, data fusion or whatever, image processing. And an additional really hard stuff is how to determine the safety rules in that case. You can just say, okay, I am in close vicinity of the barbecue, I just stop, or the user, but you have also to integrate self collision and things like that. So if you want to build a safety layer or a safety monitor, you have to think of what are the observation means, what are the safety rules, and what is the reaction of the system, the recovery you are putting it. Okay? This is the example of the barbecue robot, but it's exactly the same with autonomous cars because we are talking about that. Okay? It is safer in case of a failure of the whole system to decelerate, or sometimes it's better to accelerate or to change the lane and so on. So you can see that this issue of putting the system in a safe mode is not so obvious. And this is why we are working actually on this idea of building safety monitors. For years and years, actually, what you can find out, I just switched that, sorry. I will come back after that. What you can find, this is exactly what I said about sensing the logic, the safety rules, and actuating and putting the system in a safe state. So you can find that in industrial robotics, you have those yellow chain, which are certified components. So you buy them and you have probability of failures which are suitable for safety critical systems. So you can buy sensors, the logic part, and the actuators. But it's only for very basic functions, like shutting down or cutting the power or things like that. But now, building more complex cyber-physical systems will lead to more complex safety rules, more complex observation, and more complex actuators and safety recovery mechanisms. In order to do that, of course, just in the idea of building a separated monitor, so I'm calling it safety monitor, but it's just the idea of having an active component which is separated from the main control software. In the main control software, you have exactly what you have seen presented by Walid just before. So you have control loops because you have all the sensing information and so on. But the safety monitor is not aware of all this stuff. The safety monitor is only focusing on safety. And we were what he was talking about models or abstractions. And here it's really important to separate what are the models used for the main control, and you have change of modes, and then you have control laws implemented and so on. And what are the models for the safety part? They might be the same for the specification, but at some point, because you need to completely trust this device, you will have to avoid many, many technologies that are used for the main control software. And to avoid those technologies today is, for instance, avoiding image processing. A safety system is not built today on image processing. They're starting to try to make some planes land based on image processing and things like that, but it's really, for the moment, we do not have enough confidence in such technologies to put them in safety monitors. So what is the idea of building a safety monitor? It's to find the safety rules associating observation and intervention, which is basically the sense and control and act as you can find in control theory. But what you want to preserve is some safety properties. The same we have just discussed. And with those safety properties, something which is really important is also the possibility for the system to realize its mission. For instance, if you just say, okay, I reach a very low speed just to be safe, and then you have to wait for 5 hours to get your barbecue ready, it's not acceptable. Or if you just stop every 5 minutes to put the system in a safe state, it's not acceptable. So it's why you have to find out a balance between safety and functionality. So we call that permissiveness in the sense of reachability of states, actually. So you want to reach some basic states and basic functional states. So what are the main concepts of that? A very simple view. Let's say that in your system you have catastrophic states. The speed is over the limit, or the robot is moving in the close vicinity of the user, or whatever. And we have non-catastrophic states. So here you have a safety invariant which is respected, and on the other side, on the catastrophic state, it's not respected. A safety monitor is always built on the same idea, is let's define in the safe state, in the non-catastrophic state, a region which is safe, and another region which is what I call warning states. And each time you are leaving a safe state that could lead to a catastrophic state, you can guarantee that you are reaching a warning state. So you can perform a reaction before getting into the catastrophic state. Let's say for the speed, for instance. For the speed, it's quite easy because the margin, if, for instance, the maximum velocity is like 3, you just said, okay, I'm taking a margin, and each time you reach this margin, you can engage your recovery mechanism, okay? So this is what is called what we call a safety margin. It's the distance between the safe state and the catastrophic state. Let's take this very not so simple example. Let's consider that we have this mobile robot with an arm, and in this factory, one identify hazardous situation is that the robot is going through the factory with the arm extended. Because usually the movement is just, You just stop and you just pick and place some pieces and then you move around, but the arm folded, so folded and unfolded. So you get this situation, which is the safety invariant is the arm is, so R is true, it means that the arm is extended, or the speed is less than a maximum speed. Or if you want, the catastrophic situation is the complement of this expression, which is the arm is, it's folded, it's folded. So the catastrophic situation, which will be, the arm will be extended and the speed is more than V0, okay? So if we just use very basic, and this is what I want you to do after that, if we just use very basic logical formulas like this, you can represent actually the states based on this formula with those two variables V and R with different with the different here values. So R can be true or false, and the speed can be less than V0 or max or more than V0. So you have those four states. And here the catastrophic state is when the robot is going fast and with the arm unfolded. Okay? It's okay, or if you don't understand at this point, you can. Okay, this is the red one, catastrophic one. Okay, I'm starting here. The arm is folded, and the speed could be between 0 and the maximum. So here there is no margin. So how can you detect that the system will not, and how can you just cut this transition to avoid that the system, for instance, is going fast and then the arm is extended? Or how can you guarantee that while the system is going slow, I mean between 0 and V0, how can you guarantee in case of a failure that the system will not go directly more than V0? It's not possible. If V0 is a value of 3, for instance, if just going 3 and then there is a failure, it could lead to 3 and more than 3, 3 and dot 1, and this will be catastrophic. So here you cannot guarantee that. So what we have to do is to include safety margins. So here, for instance, we just include the safety margin on the speed. On the speed is, then I have the first one, so it's just a partition of the states, and say, okay, between 0 and V0 M for margin, and then you have inside the margin between V0 minus V0 M and V0. You have another one which is this state between V0 more than the maximum speed V0, and so on. So then you have included those 3 warning states, and here on this very toy example, you can see that the catastrophic state is completely surrounded by warning states. So in that case, what you want to do is to perform a recovery mechanism, or what we call an intervention. You can trigger an intervention in those states to avoid to reach this state. So how can we avoid to reach this state? We have to cut all these transitions. It's not so easy. What is the mechanisms that could lead on the fact that you can reach here, you can trigger an action that when you're entering in these states, that will avoid the robot to go too fast. So if you want to avoid the robot going too fast, you can just brakes, engage brakes. Okay. So if you engage brakes here, you will cut this transition. Okay? But if you are coming from here, and you engage brakes, you don't know if you are at the end, I mean, if you are very close to V0, then you cannot guarantee that you can stop the system before reaching a maximum speed. So it depends also from where you are coming. I'm just taking this very simple example because actually I have seen some safety rule in safety device that has been implemented without any process, just based on expertise, and there were some errors actually because some situations were not completely covered. If you have just the brakes, how can you guarantee that when the system is going fast, how can you guarantee that you will not deploy the arm in case of a failure and lead to a catastrophic state? In that case, it depends. If you have a mechanism that is able to detect that the speed is fast, and then you can block the arm while the robot is going fast, then you can cut the transition. But it means you have a secondary mechanism, a second safety mechanism, which is block the arm. Okay? Okay, this was for the very basics. If we just engage brakes while we are entering this stage, for instance, you can say, okay, each time my speed is coming into the safety margin, I just engage brakes. Then surely your system will not be able to reach that state because you will engage the brakes here while the system is going fast, but in the margin, I mean, and you engage the brakes, so the system will stay here or go back in the safe state, and you will never reach that one. So I want to make it clear that once is, okay, if I trigger some safety actions or some intervention, I can cut some transition, but I can also cut some transition to other warning states. So I will reduce the possibility of my system. Because the safety monitor is always monitoring the main control system. It does not detect that there is a failure, it just detects some situation. So in that case, it will stop the system. So it's why I said, okay, we have to build something safe, cut the transition, but not cut all the transition if some states are available or are required to perform some functionalities. Okay, this is the basic idea. Now, how to do that? Okay, by hand is quite possible with very simple models like this. But I will show you some models. At some point, you have 3, 4 variables like this, and 3 or 4 possible intervention, and then it completely explodes. It's not possible at all to find out the solution, a good solution. Okay? So I will not go into the details of how we are doing and what the tool is doing, how the tool is doing that. I will just mention that if you want to use the tool, you will have to define and to use a formalization to describe the effect, and I will show you a very simple example. The intervention may have some effect, but also have some precondition to perform the effect, and also some sequential precondition to guarantee the intervention. Just as I said before, it may depend on the path you are following to guarantee that the system will remain in a safe state. So, this is what I said before. So SMOF is a tool. It's for safety monitoring framework. The very basic of this tool is if you are able to model those invariants, the intervention and the observation which are linked to the invariants, then there is a tool to synthesize those safety rules, which are safe and permissive. Of course, at the end, once you have performed all the safety rules, it's very important to check also the consistencies between the safety rules, because at some point in your model, you may have some rules saying, okay, you have to reduce the speed in this situation, and other safety rules may say, okay, you have to accelerate in the situation, or maybe doing different things, so you have to check the consistency. And once you have done this, you have to implement the safety rules in the main monitor. So for that, we are using a model checker, which is a new SMV for the two of you who are using formal methods. And this is a basic model checker. And we are using a very classical branch and bound algorithm with some simplification. So I will not go into details on that. So these are examples. So what I propose you is to simply have a look on some oops. So I have 4 examples. I'm not sure it will be easy for you to find out and to determine the safety rules. What I want you to do is we just exchange on that. Use your paper and pencil, and I will give you some very basic example. And according to that, you will have to find out how to represent the observable, find the safety margin, and trying to find if it's possible, and we will discuss about the possibility of triggering a safety action or an intervention. So we need a safety invariant, we need observables plus a safety margin, and we need a model of interventions. And once we have that, we have to determine the safety rules. So I took the simplest one at the beginning, which is linked to the throwing sausage case study. That one is not throwing sausage, but it's just the speed of the robot. And we don't want this robot go faster than Vmax. So the catastrophic state is V should be less than Vmax. Okay? So what is the safe state? So the observable, it will be easy. It's only the speed, V. Okay? So we have 3 states here. What is the catastrophic state? It's written down. Then, what is the safe state? Less than Vmax, but then we have to split it. Minus the margin. So you should have 3 states. The safe states between 0 and the margin, the warning state in the margin, and the catastrophic state, which is more than the Vmax. Okay? 3 states? This is what we got. So less than the margin, in the margin, and more than the Vmax. And we said, okay, we are using discrete variables to describe those 3 sets. 0 for this one, 1, and 2 for the catastrophic state. So this is exactly what we got here. Right?
Can you take off your badge because it's scratching?
Oh, yeah. Sorry. If we, so of course, we don't need this approach. You already know what is the safety rules you want to implement. It will, you can imagine what will be the safety rules here to implement. It's just an if something, then do something. If the system is in the margin, you just engage the brake. Okay? This is very simple. Just to show you that, okay, we just represent so the effect of the braking intervention. So next V is different from V plus 1. And in that case, we can do it by hand. We just engage the brake. So brake flag means just engaging the brakes is done in when V is 1. Okay? So this is really the simplest example we can find out. Is it clear? Yeah? You want to try something a little bit more tricky? Maybe a little bit related with the sausage. A gripper box So it's coming from the same case study as in the slides. So you have a robot in a factory holding a box with PC inside. And a gripper box must not be tilted more than alpha 0, for instance. Okay? Otherwise, you are just spreading the materials. So here, what I propose you is to determine, I will give you the hint because it's not so easy, but there are different solutions. What are the observables? What are the safety margins? What are the possible interventions? And what are the safety rules? And you will see this on this very simple example. This actually, it's not so easy. It's not coming here. You can imagine. What is the safety rules you can imagine as an expert in robotics, for instance? Now let's say you are all experts in robotics. So I'm holding a box, and I don't want that box go more than this angle. What can I do on my safety monitor?
You can add like a gyroscope sensor, something like that.
Sorry?
Gyroscope sensor, or something to measure.
You need to observe. So what are you going to observe? Alpha? Yeah, the angle. And what is the safety monitor is going to do? You don't want that alpha is too high. So you can put a safety margin on alpha. And that's it. And say, okay, my system will never fail like this. But actually, the gripper can have several positions while it's closed or even open. And for some movement, it's not possible to keep the gripper always in this alpha position. At some point, you can have something like that or whatever. So you have to consider not only this position, but also the fact that it's closed or open, holding a box or not. So at the beginning, the thing that was implemented was, okay, I need a margin on alpha, and then when alpha is more than alpha 0, I just stop the rotation. And at some point, the robot just put in the movement his gripper in more than alpha and try to grip something where alpha was more than alpha 0. And the box just turn around. So it's not so easy. So what we have here is, this is a representation of the different states that can be useful. At the beginning, we had more four states like that, but we can simplify with only 3 states: closed, open with nothing, and closed holding something. And we have the margin in alpha. Okay? So considering that, you can try to draw all the states of the system, the catastrophic and the safe state. Do you think you can do that, or you want some hints? It's just a combination of all of this. G0, G1, G2, with alpha equal to 0, 1, 2, which leads to how many states? It's just a combination. How many states do we have here? 9? Yes? 9 states. Just the combination of that. 0, 0, 0, 1, 0, 2, and so on and so on. So with only those 2 variables, and for a moment we don't speak about intervention, we do have 9 states like this. I didn't represent here the transition because you will have all of this. And I didn't speak about the fact that on the previous example that you might have change of the 2 different variables at the same time. Okay? So can you recognize here the hazardous state? The hazardous state, the catastrophic state is when I hold a box and alpha is more than alpha 0. G equal 2 and A is equal to 2. Okay? The safe state here means that I cannot switch from a safe state to a catastrophic state. I should always go in through a warning state. So here, G is equal to 0, A equal 2. For instance, here, so I'm close, and, but I am more than alpha 0. So it means that the robot can move in every position when the gripper is closed, okay? But at some point, when the gripper is open, I can move around, but I'm in a warning zone. Why it's in warning zone? Because I can try to grip a bottle, for instance, while my angle is more than the expected one. So I can try to grip that one, something like that, okay? So it's why here we have this warning state. That makes sense? Yeah? So here, I have represented some examples of interventions. If you are able to stop the rotation or to block the gripping with some effect, which are, for instance, the next value of the rotation is different from A plus 1, and the next value of G is different from 2. It means that you can apply some safety rules in this example, like in the state G equal 2 and A is 1, here, you just tape the rotation, stop the rotation, for instance, so you avoid to trick this transition. And blocking the gripping is to remove those transitions from those warning state to this catastrophic state. So let's take, for instance, this one. G is open, and you are in the margin. So you just block the transition to grip, to close the gripper when you want to catch an object, because you are already in the margin. So the basic idea here, the safety monitor, when you are already in the margin of the rotation, you don't want to grip something. So we are really close to control the main controller, but it's only focusing on safety at this point. What is really, really difficult here is to find out with the expert, is it possible to observe this and to put sensors to be sure that I observe that the gripper is closed with nothing, or open with nothing, or closed with something. So you need an observer or a sensor to detect those situations. You also need a sensor to detect that you have a rotation. Okay? So sensors, for instance, if it's closed or if it's open, might be, for instance, a contact sensor here or a position sensor here. But here, to detect that you have something in the gripper and to have something that you can trust with a very simple technology is not so easy. You may use some moment or sensors here, or a contactor, or pressure sensors, or something like that. But if you want to use such rules, at some point you need those sensing information. Okay? I think I would say that it's at some point to find out the complete safety rules on such examples. It's not so complex, but what is really important for you to understand, if you want to build some safety monitor for whatever system, whatever situation, if it's mobile robots or autonomous cars or whatever, the safety properties are based on observation, a safety rule and an intervention. And you have to find out the safety rules on that. Okay, what time is it? I don't remember. I still have time.
You have a few minutes.
A few minutes, okay, great. So you can find out that the idea here at the beginning, which was, okay, when I'm in the margin, I just stop the system, is not enough. And I want you to share that. I will just show you this example, which could be, actually it could not be done by hand. It's just the collision avoidance. The collision avoidance is basically having a system, and this is a very simplified view. You have a warning zone and the robot zone. So the warning zone around and the robot. And you just want the robot stop when there is something in the warning zone. So the safety rules is quite basic. You can imagine that you can implement a safety rules, which is when there is an object in the warning zone, you have lasers all around, I just stop the robot. Right? Do you think it's enough? Is it safe? Can you imagine other situations that might be covered by that?
It's not available all the time.
It's not available, what?
You said it breaks whenever.
It breaks whenever there is an object entering in the warning zone. Okay? You just engage the brakes. But in which situation, actually, there are other situations. And I have seen it, actually, on a robot. So you have some lasers around, which are mounted here. And to detect the collision, you have bumpers here. Okay? And at some point, when you detect that there is something entering while the robot is moving, there is no problem. But when the robot already stop, and there is someone here touching the robot, actually it was not detected in the warning zone, and the robot start while someone was touching the robot. So it was a very simple rule, but actually it just started the robot. It was for an agricultural robot, and there were a part where the human can intervene to change the tools, and he was changing the tools, and then the robot just started, because the rule was just for when I'm moving, if I see something, I just engage the brakes. For this, so the catastrophic is catastrophic state is there is an obstacle touching the robot, and the speed is more than 0. This is a catastrophic state. This is what you want to avoid. And if you are using that, you just have to model your system. So this is one way of modeling that. You can also use X and Y to describe the position and so on, but it will be more complex. So this is a very simplified view. And if you just enter this observable in the system, then you can generate some safety rules. But what is important once you are making your model, it's also to describe when there are some dependencies between those values. And here you can understand that when there is an obstacle here, it cannot appear somewhere, and it should appear in the warning zone. So the intervention is next v equal to 0, and the safety rule then is the generation, is the fact that you have something touching the robot and the speed is 0, or you have something in the warning zone even if the robot is not moving, so you engage the brakes. So you are sure, even if there is some failures, that the robot will not touch will not start and make a collision with the human. And the last one, which is there is nothing touching the robot, but there is something in the warning zone, and in that case, you just engage the brakes. Behind this, so if you download the tools, you can have those models. They are provided as examples, so you can make and model the safety rules. And what you can do is, at this point, make an intervention also see that actually, just to show how it could be complex after that, the margin here, when you are moving, is acceptable only if the speed is less than a speed max. Because otherwise, if the robot is going very, very fast, in case of failure, even if you have a warning zone, you will have a collision between the robot and the guy, because you don't have enough time to engage the brake and to stop the system. So once you are working on this example, it means that you have another catastrophic state is that the speed is more than another speed limit, which is determined by the safety margin. And this actually leads to another catastrophic state and another safety rule, which is engage the brake whenever the speed is more than this speed or in the margin of this speed. And at the end, it means that you get a complete description of this speed with 4, not 3, but 4 sets, depending on this speed max and the margin, and the final safety rules depending on those different values. So this example actually is not too complex. It's more than, I don't remember. I think there are something like 12 states. But it could be done by hand, but it could lead some errors, and actually there were some errors at the beginning. And if you want to go further on that, we do have another example which is based on a project we had with Martin, CPS lab project. So you can download the tool and the complete model of that. And this robot actually is a robot able to monitor some lights in an airport for the landing area. So you have low lights and high lights, and you have to check if the light is okay on all the airport and going around. So you might have low obstacles, high obstacles, you have lasers around, and in that case, without any tool, it's not possible to find out the safety rules that you want to implement in the safety monitor. Okay, that's it for the safety monitor. If you have some questions.
Jeremy, Valid said Java was the only caveat for installing Academ. So what is the only caveat for installing your tool? What do you need?
Linux, at least 16.04, and Ubuntu, of course, Linux Ubuntu 16.04, and a version of new SMV, which is a model checker, but it's provided actually with when you are downloading it, it provides a good version of new SMV. I didn't test it on Ubuntu 18, but I'm pretty sure it's okay because it's very basic C programming, and so you can recompile everything. It's just exploring a system state and find solutions. But it's not providing any fancy ergonomics, and it's just command line tools, and you get some files with results. And the results are expressed in terms of logic, a little bit as I have presented here, but in terms of logic formulas, actually, with like this.
Okay, thank you, Jeremy. So we definitely need a leg stretch. I think everyone needs a little leg stretch.